Everyone, it's Blake. So this is my latest in the machine learning series that I've been doing. I've gotten a lot of comments and thumbs up, so thanks for everybody who's been watching. Appreciate it. I didn't actually expect many people to pay that much attention to it, but it's great to see that folks have been watching these. So this is my latest. I have the same bot as last time. In this case, I have changed it so that it is in continuous space as opposed to discrete space. And that's important for a couple of reasons when using this tool set. So I wanted to kind of go through some of the code, show people, because people have started to ask, and then I'll put my GitHub out there if people want to check out my GitHub. I have to commit the latest, but it's currently training, so I'm just kind of leaving it alone and letting it do its thing. And we can talk about that in a bit. So once again, we have our uber simple robot, right? We have a rotator at the bottom, and then this joint here is a bender. So it's a rotator and a bender, and that's all it does. It looks around. The previous version was a discrete space robot. So the idea was that if you press left, it would go left. If you press up, it would go up. If you press down, it would go down. And that's fine. The problem with the discrete space input when using this tool set is that you have to clearly delineate every combination of options. So you have to say, do nothing, turn left, turn right, go up, go down, turn left and up, and left and down, and right and up, and right and down. So that's not great. And then you start thinking about, well, we want to get to the point where we're at 6 degrees of freedom, and now all of a sudden you have a real problem because your combinatorial math says that things get bad pretty quickly. So, with 2 degrees of freedom, not a big deal. However, in a continuous space application, this tool set will allow us to have multiple inputs, so one input per dimension. So in this case, we have one for the rotation and one for the amount of bend, negative 90 to 90. So we have to pose the problem a little differently. So in this case, what we're doing is instead of having a left and a right button, there are an array of buttons which say, to what degree do we bend? And we actually let the machine learning algorithm pick any value from 0 to 1. 0 being minimum value, 1 being maximum value. And it will, figure out, if it's a 180 degree bend, then 0 means no bend, 1 means bent, well, opened up all the way. And 0.5 is going to be in the middle. So that allows us to have the same kinds of motion, but have it in such a way that it's not a combinatorial nightmare to try to tell, things like, yes, we want to bend here and rotate there and bend this way and that direction all at the same time. Because robot arms can do that, and we do that all the time very naturally. So I just didn't want to have to enumerate all of the possibilities. So you'll see this is my Unity project. We haven't shown this much. Main camera, nothing special there. The robot arm environment, this is a self-contained environment. I'll get into that. Light, nothing important there. Environment builder, I'll talk about that in a second. And then here is the standard Unity robot, Simple Robot Academy, or well, their academy. So I have the Simple Robot Academy. In this case, I have the max steps set to 1,500. So this is a timed game, right? You have 1,500 steps to get as many points as you can. And then there's a width and a height. And in the robot brain, we have the state size is 8. So that is going to be the number of parameters that we provide as the state. So bend amount, rotate amount, target location XYZ, and hand location XYZ for the complete state. Action size is 2, so this is how much do you bend, or 1 for bend, 1 for rotate, that's it. Memory size is 24, I haven't actually played with that since the last time. And again, here you'll see the action descriptions, rotate and bend. I am not using their input bindings for the continuous player actions. I just have it in my fixed update for the times that I play with it. It's not great, but, it works. So if I were really paying attention, I could actually bind it to like a joystick, and then that would also have that continuous state, and then it would be joystick control, and for 2 degrees of freedom, that would feel very natural. But you can see that I can move this around and back, and you'll see that it always returns to 0. That's not actually my code doing that. Oh, and I got one. What's happening is because this continuous player actions is firing, it's just constantly saying, hey, you know, what do you want to do? And it's receiving no input, and so it's setting everything to 0 constantly. So the two are fighting a little bit, which, again, it's suboptimal, but really the main idea of the player mode is to just make sure that your problem is solvable by a person before you ask a machine to go do it. All right. So this robot arm environment, what I've done is I've encapsulated all of the aspects of the game in a single prefabbed game object. And that's actually really important as we move forward. But the idea here is, excuse me, everything we need to run the game is here in this prefab. I could turn off everything else. Well, it might break, it might not. Well, if I turn off the light, then we won't be able to see anything. Well, there should be enough ambient light. We'll still be able to see. Oh, we can see silhouettes. It'll be great. Can't turn off the camera, of course. And then we run and we see, yep, it works. And now we don't have the conflict between the two where it's resetting because I've turned off the Academy. Right? And so I can play my game in the dark with everything turned off again. So totally encapsulated environment, and that's important. We'll get into why that's true in a second. Let's turn on the light. I'll turn on the Academy later. Score, very simple beastie. So it just has a little mesh renderer and a text mesh, and it receives events, and then we'll update the score. The target we have seen in the previous version of the game, so this is just a ball, and it randomly appears on the perimeter of a unit sphere, or unit hemisphere, upper half, right? And so standard collider, standard renderer, nothing special. And then the target script here, pretty short script. And so when it gets hit, so this on hit, right, on trigger enter, so it is a trigger. On trigger enter, then it invokes a Unity event, and it says, what do we do? And so we have all of the things that we do. In this case, the only thing that we do is we report to the game manager, right, up here, that the target has been hit. And so that game manager will then move the target to a new location and increment the score. Yes, so this game manager here, again, on target hit, so it receives a target hit message and then actually rebroadcasts out and says add reward, increment score. And then when the game is reset, it also resets the score. This game manager just keeps track of all the other little components in here and what's the spawn distance. It's actually 1.15 meters away from the origin of the rotator instead of 1 exactly, because the ball has some size to it, right? And the hand, like, we keep track of that just so that when we pass the state and we say, hey, where is the hand being that ball up here, you know, it's just really convenient to have a placeholder so that we can just go, oh yeah, grab the hand's position and pass that on. Let's see. Rotator's a little more complex, so this is where I have all of my key bindings to move it around and up and down, and again, this could be better. We could use a joystick or something. The rotate speed and bend speed, those are kind of important. Use rotation speed. So one of the things that I had a problem with, and I would love if anybody has any feedback or thoughts, is I don't have a good mechanism for queuing actions. I would really like to have, you know, these arms be animated smoothly when the computer is playing them so that it has to figure out kind of the best way to get to the ball so that there's a time penalty. What I do is when I'm training, I've turned off the rotation speed so that it at least understands the relationship between the target position and the hand position and that they have to be very close to one another to earn the points. But ideally, I would like it to know that there is a cost for the rotation speed. That works well in a discrete environment, but I definitely found when I moved this over to continuous environment, because of the amount that I was just randomly moving around, it wasn't actually getting the targets at all, because it was issuing commands so quickly that nothing had really happened by the time that it issued the next command. So I'd love if somebody had some ideas on how do we effectively, especially if they have an example, that you issue a command and then you wait for that command to complete before you do your next evaluation and issue another command. Because they also have, I did see in the toolset where you can just wait for a set amount of time, but I didn't want to do that because I wanted to reward where if you make a bunch of really quick motions, that may be more beneficial than one longer term motion. So let's see here. And again, the first rotator and the first bender, I have those marked as first because I am planning to have more. The rotation min-max, 0 to 360, bend min-max, negative 89 to 89, so it's 178 degrees of bend, not 180, just because I was hitting an edge case where it was doing some weird stuff, so I just shaved off 1 degree on each side, and that's fine. The desired rotation and desired bend, these are just kind of output variables, so that as I'm playing with things, I can pay attention to see if it's doing what I think it should be able to do, or it's doing what I think it should want to do. All right, pulling up some code. So reference to the game manager, add a reward, step through, right? If it's continuous, then we get 1 action rotation from the action array, and then we also get the bend action from the action array, and we set the rotation and we set the bend. That's all we do. And then if for some reason things are set as discrete input, I just output log, and then this is where we collect the state and say, hey, yeah, here's the target transform position. Also, when I'm passing in the target transform's position, anytime I pass machine learning stuff, the target's position, I do it relative to the origin of that arm so that I can have multiple of these going all at once. I'll show you how we do that in a second. And so it's always the target's location in relation to that encapsulated game. All right, so that's why I encapsulate the game, so that I can have 20 games going simultaneously. Also the rotate amount, same thing, right? So where's the target? How much are we rotated? How much are we bent? And where is the hand? Those are the big questions about the state. That's what I think the machine learner is going to need to know to complete this. Again, the target script we've already gone over. Simple Robot Academy. Again, we just have some mapping. Because we cross over, we go from 270 to 90. So because we crossed that 360 0 threshold, I just remapped to negative 90 to 90, so it's a little more clean. So when we get a bend command, yeah, here's all the key stuff, right? So whatever button you press, it goes to a relative thing. So anywhere from 0 to 1, because we're in that continuous space. And in this case, for the rotation, I just made sure that I went to 0.875 because 0 and 1 are the same thing, right? 0 degrees and 360 degrees are the same, so really this goes up. This has, 8/8, right? But I'm just not repeating at 360, as opposed to the bend, where since we're going from one side to the other, they're not, the beginning value and the end value don't equate to the same. So I have 9 here and 8 there. So rotate, basically, we find the rotation of the rotator, and then this desired rotation that is set in our set bend or set rotation. And if we are animating smoothly, then we limit the amount of rotation that can happen every duration. And then if we're not, then we just rotate 100%. And again, that provides a very, very fast mechanism to just zip through a whole bunch of things. But again, I actually would prefer that we use this at all times. I just don't know how to properly wait on the next command until the current command is completed in a way that will work with the machine learning stuff. Like, I know how to do it in normal Unity. I'm just not convinced that it'll work well with the machine learning tool set that we've been given. All right, robot arm game manager again. So spawn center, spawn distance, rotator bender. So this is just placeholders. What do you do when you reset the game? Move the target within the unit sphere. What do you do when the target is hit? You move it, you add 1 to the score, and then you invoke. Call other people and say, hey, this happened. And then this is just getting a point on the unit sphere. I've already talked about that one. Simple robot decision continuous. So this is actually pretty much just copied and pasted exact. I don't think I did anything with the decision. This academy is exactly verbatim. Didn't have to do anything from there, and the agent. And then I was referencing the Ball3D agent. So that's the code that is in the game itself. So the environment builder, what that does, so what I did is prefabbed out this encapsulated environment. I'm going to turn this guy back. Well, I don't have to yet. So I'm going to disable this single environment because I have down here in my prefabs this robot arm environment. And so that is an entire encapsulated environment, just like the one that we have in place. So what our environment builder does, very simply, is we give it an environment, we give it a number of rows, number of columns, and we put some space between them. And then the key here is this brain to use, and so that is a reference here to the simple robot brain, so we will need this. And so what happens is when I have this environment builder on, it just has multiple instantiations, right? And now I'm playing 20 games all at the same time, which is not terribly great for me as a person. However, it is highly informative for computers as they learn, because actually what happens when the computer learns is it will use the same brain, so the same logic to evaluate all of these, but they are actually going to be played as individual games. So it's playing 20 games simultaneously, which should help the training rate significantly. So our simple robot brain, yeah, we already went over that. Environment builder, so the environment builder script, I mean, there's not much special going on here, right? So to wait, just a double nested loop where we're instantiating the game object, we're naming the environment so that we can find it. And then, so the real key here is in the environment, I do this get component in children and I look for the agent inside that. And so anything that inherits from agent as well. So agent or any of the agent child classes are going to get picked up by this. And that's how I'm able to assign dynamically the brain so that I don't have to do that for every single one. Very simple. It's just using the inheritance to find those agents and then assigning the brain over. And then I just continue spacing them out so that everybody has enough room. I don't want the target of one game to get hit by the hand of another game, because that would lead to chaos and sadness. All right, so that is a toward the code. And so what's going on right now is I am currently training this. Let's see here. So you can see this guy going on. Oh, here it is. So we have 20 of them, and they're zipping along. And this guy, whoop, it just hit 30 before the game reset. This one's at 15, 13. So they're doing okay. They're certainly superhuman in ability. But the training has also been a little weird. So I definitely, anytime I set up a new environment, I go over this document again, reread it, think it through, and adjust my parameters accordingly. Even still, though, the output sometimes gets it's not really random, but it sure moves around a lot. So actually things have improved since the last time I pulled this up. So we got better and better and better and better, yay! And then, yeah, okay, it goes down some, that's not a big surprise, it's, it's learning. And then it got even better, and that was great, and then it took a dip, and a bit of recovery, and then it has this major dip. And I'm not really sure what's causing this. What's interesting is at the same time, the entropy was also at an all-time low. So 49 minute, 32 second, right? And that's right here. So right when this dip started was the same data point as this all-time low in the entropy. So I was wondering if something was up with the entropy, but the entropy picked back up. And so all of the, value estimates and cumulative rewards have all likewise picked up. So it seems to have, I haven't readjusted these. So it seems to have gotten better, but our entropy has kind of petered off. And our cumulative reward, again, it goes up and down a lot. So we'll see. This isn't going super duper fast. I'm running this all on CPU. So if somebody also knows a ready way, I don't want to rebuild TensorFlow from scratch. I will if I have to, so that I can get the GPU in, but Python is not my first love. I use these tools, but I don't necessarily want to be down the recompiling from zero. So if anybody knows any resources where it's like, just grab this version of TensorFlow for an i7 and, NVIDIA GPU, 10 series GPU or something, and then it's already good to go, I'll absolutely pass that on, because that would certainly be a resource that I'm interested in. I'm sure other people would be interested in too, is if they could just go grab, the proper binary and not have to rebuild. Or failing that, if the proper thing to do is rebuild, then a great resource on rebuilding TensorFlow, because I haven't found anything. So we're going to see what's going to happen here. I really do feel like the cumulative reward here is, mirroring this entropy, that when this entropy really hits these lows, it damages significantly the cumulative reward. So I'm not really sure what all the implications of that are. I might just see if I can play with some of the entropy scores and whatnot. Or I'll just let this thing run and see what happens, because it does seem to be overall on an upward trend. But yeah, we'll see. So, GitHub. So again, I haven't committed this code yet, but you can find my GitHub at github.com/Dracolich, DRACOLYTCH. And you can find the latest on the Dracolich ML agents. I am a bit behind the master on this. 23 commits. I'm more than a little bit behind now. But I've been playing in my own little environments here, so I've gotten a little behind. I'm going to pull, I hope, tonight and get caught up just once I finish this training and I feel like everything is stable and doing what I want it to do. So from here, now that I think, and I do have, I might need to tweak some of the parameters just to, keep with the good rewards here. Yeah, we're dipping again. So the next goal is to start adding, now that we've gotten out of that, away from that combinatorial problem, more degrees of freedom, right? So we're going to have another rotation, right? So we have a rotation and we have a bend. So we've modeled really this portion of the arm, from the shoulder to the elbow, and so another bend and another rotate. So we're going to get 2 more degrees in there. And that's, well, actually, the last rotate doesn't matter yet. So next one's going to be another bend, because what that's going to mean, the problem gets a lot harder, because now we're going to be trying to touch anything within the unit sphere instead of just on the surface of the unit sphere, or hemisphere, right? Because we're not doing the full circle. So that's going to be complex. And then eventually I would like to get into gripping positions, but I know that problem starts getting really, really hard. And I don't know for some of the kind of end use cases that we're talking whether or not that's really going to be valuable. So I at least want to get one more bend in there. I'd like to add a couple more. And the other thing is that we don't have to be biomimetic, right? That's actually part of the fun part of this is when you're using Unity's inverse kinematics, it has to work kind of like a human works. Since we're using machine learning and we're avoiding the inverse kinematics, then we can start getting very creative at the anatomy and geometry of what we can do and how it'll learn and act. And so that's actually what I'm kind of really excited for, is to have some kind of like crazy, freaky robots that, you know, maybe people wouldn't really know how to control, but they can learn how to control themselves and be super, you know, I don't know about efficient, but at least interesting, right? So that's kind of where I'm going with this. And hopefully I can use that in a game or research or something. I have no idea. So that's where I am. This is where you can find my code. Again, GitHub, Dracolich, ML Agents. And that should be it. So that's a tour of everything for now. We're going to get a little more complex in the future. If you have any questions, thoughts, or hints, again, for the things, you know, if you have any suggestions on how to help with some of this action or how to speed things, make it easier for me to get on the GPU instead of the CPU to dramatically speed up the training, or, you know, anything like that. Oh, the a machine learning ML agent friendly way of doing, you know, waiting a task queue, waiting for one task to complete before going on to the next one, and only evaluating once one task is complete. So those are the big three things that I still haven't quite gotten yet, but I know somebody out there is doing it, and if not, you know, we'll figure it out together. So thank you much, and I hope you all have a great evening.